Okay, let's dive in. Think about the absolute wonder of flight. How does something as heavy as an airplane, often a large hunk of metal or these days cutting-edge composites, actually defy gravity and glide through the air safely, sometimes for thousands of miles?
It really does feel like magic sometimes, doesn't it? But behind that magic is a world of precise engineering, fundamental physics, and incredibly rigorous standards.
Exactly. And that's the mission for this deep dive. We're going to unpack a key source, a foundational chapter from the FAA's Pilot's Handbook of Aeronautical Knowledge. It's pretty dense stuff.
It can be, yeah.
But our goal is to give you the shortcut. We want to understand the essential building blocks of an aircraft, how it's designed to be safe, what keeps it up there, how you point it where you want to go, and even what the pilot is looking at to make it all happen.
And we'll use the Class-in airplane as our main example, though, many of these ideas apply more broadly across aviation.
Sounds good. Ready to get started?
Absolutely. And maybe the best place to start is how the regulations themselves define what we're even talking about.
Okay.
The rules, specifically Title 14 of the Code of Federal Regulations, known as 14 CFR, define an aircraft pretty simply. Any device used or intended for use for flight.
Simple enough on the surface, but that covers a huge range of things, doesn't it? Everything from, I don't know, a balloon to a jumbo jet.
Exactly. The handbook mentions categories, especially for pilots getting certified.
Right.
Yeah, for airman certification, they break it down into categories like airplanes, rotorcraft, think helicopters, gliders, lighter-than-air vehicles, powered lift, powered parachutes, and weight shift control.
Quite the list.
It is. But our focus, mirroring the source, is mainly on the airplane, which the regulations specify as engine-driven, fixed-wing, supported by air acting on the wings.
And you hear terms like advanced avionics aircraft now, too. What's that about?
Exactly. While not a formal certification category yet, it points to the technological shift aircraft with modern systems like integrated GPS, moving maps, and sophisticated autopilots. It's all part of that evolution we'll touch on. Okay, so long before a pilot ever climbs aboard, there's a massive system to ensure this complex machine is actually safe to fly. How does the FAA certify that?
This is really where trust in aviation begins. The FAA certifies the major products, the aircraft itself, the engines, and the propellers. This process is built on airworthiness standards.
Airworthiness standards. That sounds like the bedrock.
It absolutely is. These are detailed engineering standards, parts of the 14 CFR, like Part 23 for smaller planes or Part 25 for large transport jets. They dictate things like structural loads, performance minimums, system reliability.
Basically making sure the design is safe from the get-go.
Precisely. Safe from the drawing board.
What about aircraft that don't fit neatly into those boxes, like a glider or one of those newer powered lift designs?
Good question. The handbook points out these fall under special classes. They don't have a single dedicated standard. Instead, the FAA works with the designer to piece together requirements from existing standards that are appropriate for that unique aircraft type.
Okay, so the design meets the standards and gets a stamp of approval. What's that called?
That's the type certificate, or TC. It means the basic design complies with all the rules. Along with the TC comes the type certificate data sheet, the TCDS.
And that TCDS is public information.
Yes, you can look it up on the FAA website. It defines everything about that certified design, its approved engines, propellers, dimensions, weight limits, other critical characteristics, really the blueprint.
The source mentions light sport aircraft have a slightly different path. How does their certification work?
That's a key difference, yeah. LSAs were introduced as a more accessible category. Instead of building to traditional FAA engineering standards, they're built to industry consensus standards, things like ASTM standards.
So industry sets the bar, and the FAA accepts it.
Essentially, yes. The FAA accepts these as the basis for certification. And unlike bigger planes where engines and props might be certified separately for an LSA, the type certificate covers the aircraft as a whole: airframe, engine, and propeller together.
Interesting. So the design is good, the type is certified. Now they have to actually build the plane. How do they make sure the one being built matches the approved design?
That's the manufacturing side. Each aircraft, or even each component, goes through what's called a conformity inspection. It's a check, a rigorous check, to ensure that the part or the assembled aircraft was built exactly according to the specifications and drawings in that certified design.
And once it's all built, inspected, and signed off, it gets its final blessing, the airworthiness certificate.
Precisely. When the completed aircraft meets the design standards, the manufacturing requirements, and is deemed safe for flight, the FAA issues the airworthiness certificate.
That's the critical document, right? You have to carry that on board.
Absolutely. Must be on board for every flight. And its validity isn't eternal. It stays valid only as long as the aircraft receives the required maintenance and inspections. It's proof the aircraft met standards at the time of certification and continues to be maintained to those standards.
I've seen they come in different colors, white and pink. Is there a difference?
Just categories, really. Standard certificates are white, typically for aircraft certified under the more common rules like normal, utility, transport, and those special class aircraft like gliders.
On the pink ones.
Special certificates are pink for categories like light sport, experimental, restricted, or things like temporary ferry permits.
So that whole intricate process is about building foundational trust that this complex machine is structurally sound and safe before it even rolls onto the runway.
It really shows just how layered the safety system in aviation is, starting right from the design and manufacturing. It's quite remarkable.
All right, so we have a certified airworthy aircraft. Now for the real magic. How does it actually fly? Our source gets into the basic aerodynamics. What are the fundamental forces that make this happen?
Okay, yeah. If we boil it down to straight and level, unaccelerated flight, there are four main forces in balance: thrust, drag, weight, and lift.
Let's picture that. What's thrust doing?
Thrust is the forward active force, typically generated by the engine and propeller or, jet engines. Its job is to move the aircraft forward through the air and overcome the force trying to slow it down.
Which is drag.
Exactly. Drag is the rearward force. It's the resistance the air puts up as the aircraft moves through it, from the wings, the fuselage, every little part. Drag opposes thrust.
Weight is pretty intuitive, gravity pulling down.
Right. Weight is a total force pulling the aircraft down due to gravity. The aircraft structure itself, the crew, fuel, cargo, it acts downwards through the aircraft's center of gravity.
Ah, the CG. We'll come back to that.
Yes, definitely. And it's the force that lift has to overcome.
Which brings us to lift, the critical one.
Lift is the upward force generated primarily by the wings. As air flows over the specially shaped wing, the airfoil, it creates a pressure difference, lower pressure on top, higher pressure underneath, that pushes the wing upwards.
So it's the wing shape doing the work.
Fundamentally, yes. Lift opposes weight and acts perpendicular to the direction the aircraft is moving through the air, through something called the center of lift.
So in that steady level cruise, it's a delicate balance. Thrust equals drag and lift equals weight.
Precisely. A state of equilibrium.
But aircraft don't just fly straight. They pitch up and down, they roll, they turn. How does a pilot control all that movement?
Right. An aircraft moves in 3 dimensions, and control is all about rotating the aircraft around imaginary lines that pass through its balance point, that center of gravity again. These are the aircraft's axes.
3 axes. Tell us about them.
First, the longitudinal axis. Imagine a line running straight from the nose to the tail. Movement around this axis is called roll, when one wing goes up and the other goes down.
Okay, like rolling a boat side to side.
Pretty much, yeah. Next is the lateral axis. This runs side to side from wingtip through the fuselage to the other wingtip. Movement around this axis is pitch raising or lowering the nose.
Up and down, got it. And the third?
The vertical axis. This goes straight up and down through the aircraft, perpendicular to the other two. Movement around this axis is yaw the nose, swinging left or right, kind of like steering a car.
So roll, pitch, yaw.
Exactly. Every control input the pilot makes, moving the stick or yoke, pushing the rudder pedals, translates into a rotation around one or more of these axes.
You mentioned the center of gravity a couple of times. It seems incredibly important. Why is that balance point so critical?
Oh, it's absolutely fundamental. This is where understanding the CG really matters. The center of gravity is the single point where the entire weight of the aircraft is considered to be concentrated. It's the point it would balance if you could somehow suspend it.
So loading the plane incorrectly isn't just about being too heavy, it's about where that weight is.
Absolutely. The position of the CG has a profound effect on the aircraft's stability and how it handles. The design specifies an acceptable range for the CG. It's not just one point, but a range.
And if it's outside that range,
yeah,
what happens?
It can be very dangerous. If the CG is too far aft, too far back towards the tail, the aircraft becomes unstable, difficult to control. The handbook specifically warns that you might not have enough elevator authority, enough push to get the nose down during a stall recovery.
Wow.
Yeah. And on the flip side, if the CG is too far forward, you might struggle to pull the nose up enough for a safe landing flare. Not enough pull.
So checking weight and balance isn't just paperwork. It's fundamental to controlling the plane safely.
It's absolutely crucial, and pilots have to consider how things like fuel burn change that CG position during the flight. It moves as fuel gets used up.
Okay, we've got the forces, the control movements, the balance point. Let's look at the physical structure itself. What are the major components that make up an airplane?
Well, most airplanes, from a small trainer to a large airliner, are built around 5 main parts.
Give us the rundown.
Okay. You've got the fuselage, that's the main body, the wings, the lifting surfaces, the empennage, the tail section, the landing gear for operations on the ground or water, and the power plant, the engine and propeller system.
Let's start with the fuselage. That's the central cabin part, right?
Right. The fuselage is the core structure that houses the crew, passengers, and cargo. It's also the central connection point where the wings, tail, and often the landing gear attach. It holds everything together.
Our source mentions how they've been built over time, from simple frames to complex shells. Tell us about that evolution.
Yeah, if we connect this to the goal of efficiency, the evolution makes perfect sense. Early planes used open truss structures like a welded cage of tubes, often wood or metal, functional but not very streamlined.
Lots of drag. Creates resistance.
Exactly. So they started covering the truss, first with fabric, then lightweight metal skin. This led to what's called stressed skin construction, where the outer skin isn't just a covering, it's actually carrying a significant portion of the loads the aircraft experiences in flight.
Which evolved into monocoque construction.
Right. Monocoque means single shell. The source uses the analogy of an aluminum beverage can.
Ah.
The skin takes almost all the load. It's very efficient weight-wise if you maintain its perfect shape. But like that can, it's highly sensitive to deformation. Poke a dent in it while it's supporting weight, and it can collapse easily.
So strong but vulnerable to dents. That doesn't sound ideal for an aircraft taking bumps and knocks.
Well, it led to the most common type today, semi-monocoque. This adds a substructure, things like formers, bulkheads, and stringers under the stressed skin.
Reinforcing it.
Exactly. The skin still carries load, but the substructure reinforces it, helps maintain its shape, and shares the load. This makes it much more tolerant to dense or localized damage. It's sort of the best of both worlds.
And that fireproof wall behind the engine in a single-engine plane, that's part of the fuselage.
That's the firewall, yeah. Typically part of the fuselage structure, made of heat-resistant material like stainless steel or titanium. It's there purely to protect the cabin occupants from an engine fire, giving them precious time.
Makes sense. Moving on to the wings. We know they provide the lift. How are they attached and what's hidden inside?
Wings attach to the fuselage in different spots, high, mid, or low wing configurations. And airplanes can have one set, monoplanes, which are most common, or 2 sets, biplanes like you see on some older or aerobatic types.
Some high-wing planes have those diagonal struts connecting the wing to the fuselage. What are those for?
Those are wing struts. They help support the wing and transmit flight loads back to the fuselage structure. Aircraft with struts like that are called semi-cantilever designs.
And without struts.
That's a full cantilever wing. Most modern aircraft, especially low-wing ones, but some high-wing too, have full cantilever wings. They're designed to carry all the loads internally within the wing structure itself without external bracing. It's cleaner aerodynamically.
What makes the wing strong and gives it its shape? What's inside?
Inside you have the main structural members, the spars, which run lengthwise, often from root to tip, and take the primary bending loads the force, trying to flex the wing up and down. And then you have the ribs, which run chordwise from the leading edge to the trailing edge. They define the wing's critical airfoil shape and transmit the airloads to the spars. Stringers often run lengthwise too, just to stiffen the skin and ribs.
And that's often where the fuel is stored, right? In the wings?
Yes, very commonly. Fuel tanks are often integrated into the wing structure itself, called wet wings, or sometimes flexible bladder tanks are installed inside the wing bays. It's a good place to put the weight.
What about the movable parts on the back edge of the wing, the control surfaces?
Right. Those are the main control surfaces on the trailing edge, ailerons and flaps.
Ailerons are for roll control, making it bank left to right.
Correct. They're usually on the outer portion of the wing and work oppositely. When one goes up, the other goes down. This changes the lift on each wing differently, causing the aircraft to roll around that longitudinal axis.
And flaps, they look different.
Flaps are usually on the inner portion, closer to the fuselage. They extend downward simultaneously on both wings together. The handbook points out their main purpose is to increase both lift and drag.
Why would you want more drag?
It allows the aircraft to fly slower without stalling, which is essential for safe takeoff and landing approaches. They basically change the wing's shape temporarily. There are various types like plane, split, slotted, Fowler. They all achieve this effect in slightly different ways.
Okay, back to the tail of the empennage. Sounds fancy.
It just means the entire tail structure. It consists of fixed surfaces, the vertical stabilizer, the fin that sticks up, and the horizontal stabilizer, the flat part. These provide stability.
And then the movable parts that control the aircraft.
Attached to the vertical stabilizer is the rudder. Moving the rudder pedals controls yaw, moving the nose left or right. Attached to the horizontal stabilizer is the elevator, controlled by moving the yoke or stick fore and aft, which controls pitch, moving the nose up or down.
And what about those smaller tabs I see sometimes on the back of the rudder or elevators?
Those are trim tabs. They are small adjustable surfaces controlled from the cockpit, usually by a little wheel or switch. The handbook highlights their purpose: to reduce the physical pressure the pilot has to hold on the controls.
So you don't have to constantly push or pull.
Exactly. You trim the aircraft so it flies hands-off at a desired attitude or airspeed. They basically hold the control surface in position for you. Trim tabs can be on ailerons too sometimes.
The source also mentions an alternative to the traditional elevator setup.
Ah, yes, the stabilator. Instead of a fixed horizontal stabilizer with a movable elevator hinged at the back, the entire horizontal surface pivots from a central hinge point.
The whole tailplane moves.
The whole horizontal part, yes. You control it with the same fore and aft movement of the control wheel or stick as an elevator. Pull back, the trailing edge pivots up, nose goes up.
And it has something called an anti-servo tab. What does that do?
Yes, a stabilator nearly always has an anti-servo tab on its trailing edge.
Yeah.
What's interesting here, and kind of counterintuitive, is that it moves in the same direction as the stabilator itself.
Same direction. Why?
Its main job is aerodynamic. It makes the stabilator feel heavier, less sensitive, helping prevent the pilot from over-controlling pitch, which can be easy with such a large, moving surface. It also functions as a trim tab.
Clever. All right, so we can move it through the air, control its attitude. What about when we're on the ground?
That's the job of the landing gear. It's the primary support for the aircraft during taxi, takeoff, and landing. While wheels are the most common, aircraft can have floats for water operations or skis for snow.
And wheeled gear comes in a couple of main setups.
Yes. There's conventional gear, often called tail wheel or tail dragger, that has two main wheels forward near the CG and a smaller wheel at the back under the tail.
The older style look.
Right, and then there's tricycle gear, which has two main wheels slightly aft of the CG and a steerable nose wheel at the front. Tricycle gear is much more common today because it's generally more stable and easier to handle during ground operations, especially in crosswinds.
How does the pilot steer on the ground?
On tricycle gear, steering is usually done with the rudder pedals controlling the nose wheel, often through mechanical linkages. Tailwheel aircraft often use the rudder pedals controlling the tailwheel, sometimes combined with differential braking using the brakes on one main wheel more than the other to help pivot the aircraft.
Okay. Now for the go part, the power plant, what does that usually include?
The power plant typically includes the engine and propeller. The engine's main job is obviously to generate power to turn the propeller, but it's also the source for other critical systems. It usually drives an alternator or generator for electrical power, sometimes a vacuum pump for certain instruments, and in many single-engine planes, the heat for the cabin comes directly from the engine exhaust via a heat exchanger.
And the engine is covered by a cowling, that metal shell.
Right, that's the streamlined covering, usually made of metal or composite. It reduces drag, but crucially, it's also designed to duct airflow precisely over the engine cylinders for cooling, especially on air-cooled engines.
So the engine makes things spin, and the propeller turns that rotational energy into forward motion.
Yeah. Exactly. The propeller is essentially a rotating wing or airfoil. Its blades are shaped like small wings, and as they spin, they create lift, but we call it thrust in this context by accelerating a mass of air backward. That pressure difference pulls or pushes the aircraft forward.
Most planes have the prop at the front, pulling.
Yes, those are tractor types. But some designs are pushers, with the prop mounted at the rear of the fuselage or wing.
The handbook mentions blade angle and pitch are important for prop efficiency. Can you explain that?
Yeah, they are key design elements. Blade angle isn't constant from the hub to the tip. It twists. This is to maintain a relatively constant and efficient angle of attack relative to the airflow because the blade tip is moving much faster than the part near the hub.
Okay, that makes sense.
And pitch refers to the theoretical distance the prop would move forward in one revolution if it were screwing through a solid medium, like wood. These factors, blade angle, pitch, number of blades, diameter, are carefully matched to the engine's power output and the aircraft's intended speed range to maximize efficiency.
Beyond those big five components, the source also lists some crucial subcomponents that are essential for operation. What else is key?
Yes, things like the airframe itself, which is the basic structural skeleton fuselage, wings, empennage designed to withstand all the loads. Then there's the electrical system, which generates, regulates, and distributes power for everything from instruments and radios to lights, flaps, landing gear retraction, and anti-icing systems.
And the flight controls?
That's the entire system, the stick or yoke, rudder pedals, cables, push rods, pulleys, maybe hydraulics or fly-by-wire systems that connect the pilot's inputs to the actual control surfaces like ailerons, elevator, and rudder.
And of course, brakes. Can't fly if you can't stop on the ground.
Critically important. On wheeled gear, modern brakes work much like disc brakes on a car calipers. Pads squeeze a rotor attached to the wheel hub. The friction slows the wheel. Materials can be steel or often carbon composites on larger aircraft due to the heat.
And the source had that fascinating detail about their lifespan.
Right. Unlike car brakes measured in miles, airplane brakes undergo intense stress and heat during landings. So their life isn't measured in miles flown, but in the number of landings performed. A very different metric.
That is a great detail. Okay, we've covered the traditional structures, mostly metal. But modern aircraft are increasingly built with advanced materials. Composites.
Ah, yes. Here's where the cutting edge really comes in. Composites aren't actually brand new. Fiberglass saw use in things like radomes and WWII, and composite sailplanes were around in the late 50s. The first certified all-composite airplane was, I think, the Windecker Eagle in 1969.
So they've been around, but use is growing fast.
Exploded, really. The source notes that by 2005, over a third of new general aviation aircraft used composites significantly in their primary structure.
What exactly makes a material a composite in this context?
It's typically a fiber-reinforced matrix system. You have strong fibers, fiberglass, carbon fiber, which you often hear called graphite, or sometimes Kevlar, which are the primary load-carrying elements. These fibers are embedded in and held together by a matrix material, which gives the part its shape. Most commonly, that matrix is epoxy resin.
How do fiberglass and carbon fiber compare for aircraft use? What are the trade-offs?
Well, fiberglass is relatively easy to work with. It's pretty good in tension and compression, handles impacts reasonably well, and it's less expensive and readily available. But structurally, it's often heavier than an equivalent aluminum structure.
And carbon fiber.
Carbon fiber is generally much stronger and stiffer for its weight. This allows for significantly lighter structures, potentially 30% lighter than a comparable aluminum design if done right. That's a huge advantage. However, traditional carbon fiber can be brittle. Poor at handling impacts the fibers can shatter. This has improved a lot with newer, toughened epoxy resins. Carbon fiber is also more expensive, though costs have come down over the years.
So what are the big benefits that make manufacturers go through the trouble of using composites? Why bother?
One of the primary drivers, especially for high-performance aircraft like those from Cirrus, or formerly Columbia Cessna, is the ability to create extremely smooth, aerodynamically efficient, complex shapes. You can mold curves that are hard or impossible to form economically with sheet metal. This significantly reduces drag.
Better speed and fuel efficiency.
Exactly. That smoothness is why sailplanes switched almost entirely to composites decades ago. Lighter weight is another key potential advantage, especially with carbon fiber, as we said.
Any other big pros?
Lack of corrosion is a huge plus compared to aluminum. This reduces long-term maintenance costs and concerns. The Boeing 787, with its largely composite fuselage, is actually designed to maintain higher cabin humidity for passenger comfort, partly because corrosion from hitting condensation inside the structure is much less of a concern than with metal.
Interesting. And they handle flexing well.
Yes, composites are excellent in environments with repeated flexing and vibration, like helicopter rotor blades and hubs. They generally don't suffer from metal fatigue and crack growth in the same way aluminum does, often giving them much longer service lives in those applications.
Okay, so lots of compelling advantages. What are the downsides? The handbook emphasizes one as most important.
This is absolutely critical for anyone operating or maintaining composite aircraft. The biggest challenge, the most important disadvantage, according to the source, is the potential for hidden damage. Damage, particularly from impacts, might not be visible on the surface.
You mean you could have serious structural damage inside and not see any sign of it on the outside?
Precisely. The source describes how low-energy impacts, like Dropping a tool or maybe a minor hanger bump might leave no mark, or maybe just a tiny surface scuff. But inside, the layers of composite material, the plies, could have separated from each other, which is called delamination. Or the fibers themselves could be fractured, often in a cone shape spreading out from the impact point internally. The damage on the backside of the impact can be far more extensive than anything you see on the front.
Yeah, that's pretty unsettling from a safety perspective. How do you even know if it's damaged then?
That's the challenge. It often requires specialized inspection techniques like tap testing or ultrasound performed by trained technicians. The source mentions that sometimes whitish areas in fiberglass can indicate internal fracture, but often, especially with carbon fiber, the damage can be completely invisible to the naked eye. That's why expert inspection is crucial even after seemingly minor impacts. Assuming it's okay because it looks okay can be very dangerous.
And if the outer skin is punctured, especially with those honeycomb core structures you mentioned,
Right. Many composite parts are sandwich structures with thin composite skins over a lightweight core material, often Nomex honeycomb. If that outer skin gets cracked or punctured, moisture rain, condensation, washing water can get into the honeycomb core.
then that's bad.
Very bad. The water can freeze and expand at altitude, causing further delamination. It adds weight. It can degrade the core material over time. The source stresses that any temporary patch applied over damage is just to keep water out until a proper structural repair can be made. It doesn't restore strength.
Heat is also mentioned as a concern. Can composites get too hot?
Yes, the resin matrix that holds the fibers together can weaken significantly at relatively low temperatures, especially compared to metals. Many common epoxy resins start to lose strength above about 150 degrees F, 65 degrees.
That doesn't sound very high, especially sitting out on a sunny tarmac.
It's not. That's why composite aircraft are almost always painted white or very light colors, especially on the upper surfaces. Dark colors absorb much more solar heat. The handbook gives an example. A black painted wing surface might reach 220 degrees air, 104 degrees air, while an identical white surface stays around 140 degrees air, 60 degrees C. Repainting must follow manufacturer recommendations carefully. And obviously, fire damage is a major concern, as the heat can drastically weaken the structure.
And nasty chemicals like paint strippers are a definite no-no.
Absolutely forbidden. Chemical paint strippers commonly used on metal aircraft will attack and dissolve the resin matrix of composites. The source warns that many expensive composite parts have been completely ruined this way, and the damage is often not repairable. Only approved mechanical methods like gentle media blasting or careful sanding are allowed for paint removal.
What about everyday fluid spills, fuel, oil, hydraulic fluid? Are those a problem?
Generally, modern epoxy resins used in certified aircraft are quite resistant to common aviation fluids like fuel, oil, or hydraulic fluid. The handbook suggests a rule of thumb. If the spill doesn't harm the paint finish, it's usually not harmful to the underlying composite structure. Though it does note that some older or perhaps less expensive polyester resins, sometimes found in home-built or experimental aircraft, might have issues with things like ethanol blended into automotive gasoline if that's being used.
One final technical point on composites from the source. Lightning strike protection. How do you handle that when the material isn't naturally conductive like metal?
That's a really key design challenge. Composite materials, especially fiberglass and even carbon fiber to some extent, don't conduct electricity nearly as well as aluminum. When lightning strikes an aircraft, and it happens fairly often, you need to dissipate that huge electrical energy quickly and safely across the outer surface to prevent it from blasting through the structure or damaging internal systems.
So how do they make a non-conductive structure handle lightning?
Manufacturers typically embed a conductive layer into the outer skin of the composite structure. This is often a fine mesh made of aluminum, commonly used on fiberglass structures, or sometimes copper, often used on carbon fiber structures, bonded right into the surface layers during manufacturing.
Like adding a conductive skin.
Exactly. This mesh provides a low-resistance path for the lightning current to flow across the surface and dissipate back into the air, hopefully without causing major structural damage. It's vital that any structural repairs in these areas must properly restore this conductive mesh layer.
In antennas, carbon fiber blocks radio signals, doesn't it? How does that work with lightning protection?
Good point. Carbon fiber is conductive enough to act like a Faraday cage, blocking radio frequencies. Fiberglass, however, is generally transparent to radio waves. So antennas that need to transmit or receive signals through the fuselage or wingskin, like communication or navigation antennas, must be located in areas made of fiberglass composite. These fiberglass areas then need special treatment, like windows or gaps in the surrounding lightning protection mesh, to allow signals to pass through while still managing lightning protection around the edges. It's a complex integration task.
So composites bring huge advantages in weight and aerodynamics, but they clearly require different design considerations, manufacturing processes, inspection techniques, and repair methods compared to traditional metal aircraft.
Absolutely. They're enabling amazing innovation in aviation, driving new designs and performance levels. Think Cirrus, the Boeing 787, advanced helicopter blades. But they demand a completely different and, in some ways, deeper understanding from designers, builders, mechanics, and even pilots.
We've gone from the fundamental structure and materials to the physics that keeps it aloft. Let's wrap up our journey inside the cockpit. How does the pilot actually know what the aircraft is doing moment to moment?
That's the crucial role of the aircraft's instrumentation. And probably the biggest change in instrumentation over the last few decades has been the widespread shift from panels full of individual round analog gauges, sometimes called steam gauges, to integrated electronic flight display systems. The glass cockpit.
Those big computer screens replacing all the traditional dials.
Exactly. Typically, you'll see a primary flight display, the PFD, right in front of the pilot. This screen consolidates the core flight information: attitude, airspeed, altitude, vertical speed, heading. Then there's usually a multifunction display, the MFD, often located in the center of the panel, which can show a wide range of other information like navigation maps, engine parameters, system status, weather data, checklists, and more.
What's the big advantage of these digital screens?
Yeah.
Why the shift?
Well, several reasons. They dramatically declutter the instrument panel, presenting a huge amount of information more clearly and intuitively. They can integrate warnings and alerts more effectively. And, as the source points out, they can significantly increase overall system reliability and potentially safety, because solid-state digital instruments generally have much lower failure rates compared to the complex mechanical gyros and bellows inside traditional analog gauges.
But they also require the pilot to think and operate a bit differently. It's not just reading dials anymore.
Definitely. Pilots flying glass cockpits need a deep understanding of how these highly integrated systems work, how the automation functions, and how to manage the information flow. It requires strong system knowledge and robust aeronautical decision-making, ADM skills, perhaps even more so than with simpler analog panels. It's a different skill set.
Whether it's old-school analog or modern glass, the handbook categorizes instruments into 3 basic types based on what they tell the pilot. What are those categories?
Yes, the source breaks them down into performance instruments, control instruments, and navigation instruments. This applies whether they are presented as analog dials or digital tapes and symbols.
Okay, performance instruments show.
These tell you the aircraft's actual performance, what it's doing right now, the result of your control inputs. This includes key indicators like the altimeter showing altitude, the airspeed indicator showing speed through the air, the vertical speed indicator or VSI showing rate of climb or descent, and the heading indicator or directional gyro showing direction. Things like angle of attack indicators also fall here.
Got it. What about control instruments?
Control instruments display the aircraft's attitude, its orientation relative to the horizon, and power setting immediately. They are calibrated to help the pilot make precise adjustments to pitch, bank, and power. The key one here is the attitude indicator, often called the artificial horizon.
So it shows if you're nose up, nose down, wings level, banked.
Exactly. The critical distinction the handbook makes is that control instruments, like the attitude indicator, don't directly tell you your speed or altitude. They show how you're oriented and how that orientation is changing right now. You use them to set the desired attitude, and then you cross-check the performance instruments to see the result.
Makes sense. And the third category, navigation instruments.
These instruments indicate your aircraft's position relative to a selected navigation facility, a waypoint, or a desired track. They provide the guidance information the pilot needs to navigate from point A to point B or follow a specific approach path.
So things like GPS displays, VOR needles.
Precisely. This includes displays showing information derived from GPS, VOR radio navigation, and DBs, non-directional beacons, or ILS instrument landing system signals. You'll see things like course deviation indicators, CDIs, bearing pointers, range information, DME, glide slope indicators for vertical guidance on approach, and moving maps.
You mentioned GPS there. The source briefly explains it. How does that satellite system basically work for navigation?
Right? GPS, the Global Positioning System, is a constellation of satellites orbiting the Earth, originally developed by the U.S. Department of Defense, but made available for worldwide civilian use since the 1980s. Your GPS receiver on the aircraft listens for signals from multiple satellites that are in view.
How many signals does it need?
To calculate a basic two-dimensional position, your latitude and longitude, and determine your ground track, the receiver needs to lock onto signals from at least 3 satellites. To get a more accurate three-dimensional position, which includes your altitude, it generally needs signals from 4 or more satellites simultaneously.
So whether it's a panel full of steam gauges or a sleek glass cockpit with PFDs and MFDs, the fundamental job is presenting these different categories of information, performance, control, navigation to the pilot so they can understand the aircraft state and guide it safely and accurately.
Exactly right. The interface technology changes dramatically, but the underlying need for the pilot to constantly scan, interpret, and integrate information about the aircraft's performance, control its attitude precisely, and navigate effectively remains absolutely constant.
We've journeyed quite a bit in this deep dive, really peeling back the layers on what goes into an aircraft, drawing straight from that FAA handbook. We've seen the incredibly detailed certification process that builds trust from the ground up, explored the fundamental forces that make flight possible, looked at how complex structures like wings and fuselages are actually built and controlled, examined the fascinating trade-offs and benefits of cutting-edge materials like composites.
With all their unique considerations.
Right. And finally, touched on how pilots use instrumentation, whether old or new, to understand and manage their world in the cockpit.
It truly highlights the immense complexity, but also the incredible precision and layers of safety involved in getting an aircraft off the ground and through the air reliably. Every single component and system plays a vital role.
It really does indeed. So what does all this detail mean for you, the listener, as you think about aviation? And maybe consider this. When you contemplate the incredible depth of the certification standards we talked about, the evolution to materials like composites with their specific challenges, like that hidden impact damage issue,
Which is a big one.
and the ongoing shift to highly integrated digital cockpits. How absolutely paramount does a pilot's knowledge, their vigilance, and perhaps most importantly, their fundamental trust in that machine and the entire system behind it become?
That's a great point. And as the source itself suggests, exploring these concepts further through things like flight simulation or digging into resources from aviation organizations like AOPA or EAA can really bring home the practical side of everything we've discussed today. It helps illuminate the pilot's crucial role in actively managing all these interconnected systems and maintaining that trust.
A lot to ponder there. Thank you for joining us on this deep dive into the fascinating engineering, physics, and systems that make flight a modern reality.